Check this out. I've always wanted a yellow issue 4A PCB, and now I've got one, and it's broken, so we're going to fix it. This is the machine we're going to be working on. I picked it up from eBay for what I thought was a bargain. It was advertised as faulty, and we're going to see that it is completely kaput. The serial number is tantalizingly close to an issue 5, but no, it's an issue 4A, and I saw it was a yellow PCB, which is quite sought after and I really like them. The failure mode we can see is pretty catastrophic, but we're going to figure it out. Again, here's our serial number. Damn, I'd love to get an issue 5, but it's just not happening for me. I'll get one eventually. Let's get this one open and we'll take a look at the board. The keyboard ribbons seem to be just about hanging on to life. We're going to test them later, but I've got a feeling we'll end up putting a new membrane in anyway. Here's our lovely yellow board. I love these, they're so unique, and the blue silk screen as well. I'm sure they chose it just for high contrast, but I think it looks fantastic. Let's have a closer look. We have a ULA version 7 from week 28 of 1984. From looking around online, this seems to be about right for this issue of board. What else have we got? The power circuit on the right has had a DC-DC modification. You can see in the bottom right there is a capacitor missing next to the upper RAM chips, and we have this little Triforce arrangement of 2 diodes and a capacitor. I believe this would have been a factory modification. Okay, let's have a look at the back of the board, so we'll remove it from the case because we're going to be working on it anyway. They're always a little bit stuck to the case. I don't know what that is that flux? They're always a little bit sticky. Okay, let's have a look, and oh, okay, this has had work done in the past. Look at all this burnt flux, all these marks that are left. The Z80 seems to have been replaced, and they haven't put a socket in when they did it. How unthoughtful. And the keyboard ribbon connectors have been replaced as well. Let's just have a fly around up close and look at this lovely board before we get stuck into repairing it. There's our DC-DC modification, or at least part of it. There's an extra capacitor added as well, you can see it on the right. Here's our ULA. Seems to be scuffed around the corners, I'm not sure how that's happened. And some of our logic multiplexy chips are by LCAP, interesting manufacturer. Here's our blue silk screen, Sinclair ZX Spectrum 1983, issue 4A. Now we're going to get into debugging this board, but first, do you remember this thing? This is the reactive device interface that I designed in a previous video, and here's the upgrade. Yet, thanks to this video sponsor PCBWay, I've been able to prototype a one board solution for this, which will plug into the back of the Spectrum. It was extremely easy to order through PCBWay. It's basically automatic. Honestly, it's so easy, go and give it a try. I've ordered it in matte black, and here's the first prototype board. We'll be building this very soon, so watch out for that video soon. Many thanks to PCBWay for sponsoring another video. And did you spot it when I was showing you around the board? Here's the first fault that I found. I actually thought this was just a hair or something and tried to pull it off, and it didn't move. And look at that, it's a trace. A lifted trace from the keyboard ribbon connector, and oh look, it's stretchy. Never appreciated that before. These traces are a little bit stretchy, a bit elastic. You can see it's missing, and you can see that it's coming from this resistor here. If we overlay the component layout, we can see that it's R67, and we can go to the schematic, take a look at R67 and figure out what could be going wrong because of this problem. Let's zoom in, and I found it up here next to the keyboard connector. It's a 10K resistor which connects the keyboard to KB2 on the ULA. So we're definitely not going to have a working keyboard on this machine right now. Let's do a quick continuity test. So I'm going to go from the right terminal of the resistor to the corresponding contact on the keyboard connector, and there's no continuity as expected. The resistance over it is 10 kilo ohms, so we're definitely looking at the right bit of the schematic. I'm just going to check all of the other connections from the other resistors to the ribbon connector, and we find that 4 of them are working and the one we expected is not working. So what can we do about it? Well, if I was feeling adventurous, I might try and straighten it out, glue it back down to the board and restore the look of the board by putting the trace back in its place, but no, I'm just cutting it off because that seems a bit above my skill set. So there we are, there's our gap where it was. It's got a bit of a tan line. That's okay, we're going to patch it up on the back. This is where it's been soldered in, and it's a little bit ugly, it's a bit burned, and just to be safe, I'm going to completely remove the connector and just inspect what's happening underneath to make sure that there's nothing else under there that needs our attention. Okay, so look at that second joint. I honestly thought that that was the end of a leg from the old socket. So here we are, I'm trying to remove it and it melted. That was just a perfectly square bit of solder. Never seen that before. So we'll just clear the joint and move on to the next ones. We have another damaged joint here. This pad has been a bit mangled. I'm going to desperately try not to overwork this. I'm just kind of nudging it back over the hole so that when we reflow these joints, we're going to make a connection. Let's clean off all of this burnt garbage and we can make a nice clean new connection with a new connector. Being careful to make sure this is flush to the board, I'm going to solder all 4 legs in apart from the one which needs patching up. Then I'm going to take a short length of green patch wire. I'm going to solder one end into the joint which is shared by the resistor's right terminal. Sorry, bad camera angle. There it is. And the other end I'm going to solder into the open joint on our keyboard ribbon connector, and that should complete the patch. This took quite a few attempts. It's fiddlier than it looks. I'm just showing you the successful one. Now I can just push that down flat. Maybe I'll add a bit of glue later, and there's our repair finished. We can't test the keyboard yet because we know that the board just doesn't work, so I'm just going to have a quick look over before we start doing any more tests. Looking at the DC-DC mod, I noticed that C77 was missing, and I don't think it's normally missing. So I had a quick look in the service manual, looked up C77 and checked which board versions that it's present on, and it's actually not present on the later board versions. That's issue 6A boards really, because there aren't many issue 5s as we know. And just to be double sure, let's look at the issue 4A power circuit diagram. We can see C77 here going from the right terminal of R61 to ground. Now we can compare this with an issue 6A schematic, and that a capacitor is not there anymore and nothing else seems to have changed dramatically around it. So I'm going to go ahead and leave it out. Guess it's part of the power circuit modification to remove it. Alright, we know this board is knackered, so we're going to be careful when we start our testing. We're not going to apply power. We're going to measure resistance from each of the 4 corner pins of the chip shown here in the top left. That's our lower RAM chip, -5 volt, 12 volt, 5 volt and ground pins. So let's put our negative probe on something which is ground and the positive probe on each of the 4 corner pins. And what we're looking for is any values which are close to 0, which would indicate a problem. So we're in the kilo ohms on the -5 volt and the 12 volt pin. On the +5 volt pin we are getting 800 ohms or so, and the top right pin is ground, so we're going to get basically 0 there. That's what we expect. So those resistance measurements seem okay to me. I'm now happy to apply power from the bench power supply. I'm going to configure it to limit the current to something sensible. So we set it to 9 volts, we short it out and see what we're limiting at the minute. Oh, that's too high really. So let's twizzle that down to about 800 milliamps ish. Now we can apply power and we can take a look at how much current is being drawn as our first test. So let's plug it in and take a look at the readout on the bench supply. We're getting 650 milliamps. That's alright, I'm not too worried about that. So I'm happy to start measuring voltages, same pins as before. So top left we should be getting -5 and that's pretty good. Bottom left should be getting +12, that's pretty good. And I'm almost 100% certain we're now getting +5, and we are. So everything's checking out voltage wise. We can now have a look at what's coming up on the screen. And it's just like it was in the eBay listing, so the fault seems to be fairly reliable at least. It's not doing anything too sporadic or unpredictable, and it's looking to me like a Z80 failure, but we're going to do a couple of measurements just to check out what's happening with the oscilloscope. So let's apply power, clip the ground clip to the heatsink, and we'll probe each of the 8 data pins. So each of these chips in the bottom left represents 1 bit of data on the data bus. We'll go left to right and see if the waveforms look about right. So the amplitude of these is something like 4 or 5 volts, that's good. And the waveforms are all looking the same, and I recognize those waveforms as fairly normal data bus waveforms. So no worries there. Next I'm going to probe some of the address bits on the address bus, and these are all driven by the Z80. So I'm probing directly on the Z80 pins, and they're looking really crap. The amplitude of them is too small, the logic levels are all wrong, and half of them are stuck at 0. So I'm definitely suspecting the Z80 now. I'm going to unplug it and plug it back in and just test again, just to make sure that it's behaving reliably, and yeah, the address lines still look pretty bad. Now it's possible that these are getting pulled to bad levels by another chip on the board, but I'm going to start by removing the Z80 because that's a usual suspect. Now it has been changed in the past. Look at this solder job. I think I can see light through some of these joints, so I'm going to be happy to redo this. I'm a bit worried that the Z80 has died again, so I'm going to monitor this board after I've repaired it and see if the new Z80 dies. Maybe there's something else causing a problem. We're going to have to remove the heatsink so we can access the Z80 to remove it. So there's that gone. Now that's interesting. Look at that Z80, it's got a little stamp on it, RS304532. Not sure what that means. I'm sure it's just some sort of RS component number, or nothing to do with stock numbers, I guess. What do you think? Let me know in the comments. I've not seen that before. I'm going to add a bit of solder to each of these joints and then get Daisy out to remove them. I had to repeat this process once or twice and do a bit of pin waggling, being really careful with this. I didn't want to apply any force because it's already had a bit of a kick in all these joints. I did manage to get it out very smoothly eventually. Let's have a close-up look at the footprint of the Z80. I can't see any damage there. I'm going to check it though anyway by testing continuity. First of all, I'll just go around with a soldering iron and touch all these joints so that they clear out nicely, because there's a few little shards of solder left in there from when I removed the chip. Then we're going to get the multimeter out, and I'm just going to test continuity from each joint to the surrounding traces that I can see they're attached to. I don't need to look at the schematic to do this. I'm just listening for beeps and I'm just testing everything I can visually see. That way, once I sew everything back up, I'm not going to have to worry about missing anything under there if there's still a problem with the board. But everything checked out fine, so I can get on with putting the new socket in and try a new Z80. Being careful to make sure the socket is flush to the board, we can just solder it in. You've seen this a million times before, you know what's going on by now. So with the socket in, we can try a new Z80. But first, I'm going to put the old Z80 back in, just because out of curiosity, I want to look at what's happening under the logic analyzer and see if it indicates any problems. Maybe this is something the logic analyzer could be useful for in diagnosing spectrums. So let's plug it into the back. Works wirelessly, so I don't need to plug any wires in or anything. I'll just apply power and boot up the app in the PC. We'll see what we get. And we have to be mindful that it's always going to show perfect square waves which don't represent what's happening, and the signals are going through level shifters which might be hindering us a little bit. But I can see a few address lines which are stuck at 0, which would be indicative of a problem with those address lines. Although, no, I don't think the logic analyzer would be the right tool to diagnose this fault. Obviously the oscilloscope's the way to go. So let's get a new Z80 in, brand new, new stock, and it should solve all of our problems, I hope. Otherwise we're going to need to remove the ROM chip or even start testing the ULA. Here we go, plug it in. Being mindful not to leave it plugged in for too long with no heatsink attached to the 7805. Let's hold the composite cable up against the modulator casing so we can see the video signal coming out. And we've fixed it. Lovely. So we'd best do a composite video mod on this so we don't have to do that dodgy hold the connector against the case thing. So we're going to blitz this composite video mod. If you want to know how to do this, I do have a guide on the channel. Go check it out. You can find it in the video history. But basically we're going to disconnect both of the wires going into the RF modulator casing, and we're going to hijack the input pin with a 100 microfarad capacitor between the video signal and the output socket. That's about it. And put it all back together, and now we can start doing some proper diagnostics using both of our hands. I tend to go for the dandinator for this part of the job. It has a diagnostic ROM built in, although it does require a couple of key presses to kick off the diagnostic program. So if your keyboard isn't working, you can't actually get it to start running, something to keep in mind. So here we go, I'm going to run the diagnostic program, first of all for the keyboard, and let's see which keys are working. And we have a nice pattern of non-functioning keys, seems to be the first two columns and the last two columns on the keyboard grid, and we could go into detail trying to figure out what's wrong with this keyboard membrane, or we could put a new one in, which is what I'm going to do. The only machine I've got where I've been careful to maintain the original membrane was the issue 1. It was working, I haven't touched it, makes sense to me. So I've taken the top half of the case off. Fortunately, this has brass tabs, it's not glued on, which is my favourite way of assembling these cases because glue's a horrible hot mess. We'll remove the old membrane, have a little look at it, see if we can see any breaks or where our problem might have come from, get bored and throw it in the bin. And I'm going to find a new membrane from my stock. Saying that, let's look at this. It's horrible. This keyboard mat is absolutely minging, it stinks of smoke, so I'm going to go and give it a wash. Now it's looking nice and squeaky clean. While I'm at it, I'm going to give the front side of the case a bath, and now that's looking clean too. I'm happy to put everything back together. So let's have a rifle through my shelves, find the keyboard membranes, there we are. We'll pop one of these in, and we should be up and running once I've reassembled the front half of the case. We slide it into place, grab our new clean keyboard mat, pop that into place, and then we put our faceplate back on and take a bit of time carefully bending the tabs around so it's held tight to the case without breaking anything. Lovely, okay, let's put it back together and we can run some proper diagnostic tests. So far we don't know if the upper memory is working, so that's the next thing I want to test. So we're just going to start running soak tests on it, see how many rounds we get through. Hopefully it will be absolutely fine. So using the dandinator and the same diagnostic ROM. Oh yeah, quick check of the keyboard. It's definitely working fine now. Every key is working, I'm happy with that. We can move on to the RAM tests. Alright, okay, I skipped the RAM tests. Let's play a game on it. I'm that impatient. We're playing a bit of Dizzy. This tells me that the upper RAM is working, and it's much more fun than running the diagnostic soak tests, which we gave in and started running now. We got through hundreds of these, so everything seems to be absolutely fine with this board. I'm not moving on yet to do any service work on this, recap or anything like that, because after all, it's working. All I need to do really is clean the edge connector, maybe recap it, but I say it's working and everyone's divided on whether or not that's worthwhile. Maybe put a heatsink on the ULA, which is another divisive one. I should also check that it can load games from tape. Sometimes the ULAs fail in that area, although this is a version 7 ULA, so I very much doubt it. And that just about finishes the job here for repairing this yellow issue 4A board. I hope that was interesting to everyone. Keep an eye out for the next video where we're going to be building up the new reactive device interface boards. Thanks for watching.